All right, so this lesson here is really kind of an application of all of the stuff we've done so far. It involves our knowledge of molar mass and moles and how we convert between mass and moles. It involves our knowledge of how we can create a conversion factor expressing how many atoms or ions are in a particular formula. It involves our knowledge of empirical formula. It involves our knowledge of molecular formula. So really it's kind of an application of all of the stuff we've done in the last week. It's also a very important application that is used in, oh goodness gracious, to come up with specific examples. It would be used in a forensic laboratory. It would be used in a chemical laboratory trying to identify substances maybe that were produced in a particular chemical reaction, whether it's desired or not. So this is an actual practical application of the stuff that we've been talking about called carbon-hydrogen analysis. And it is essentially the determining of a chemical formula of a substance that contains carbon, hydrogen, and some other main ones like nitrogen we could also have. It could also be used to analyze things like lead. Anyway, you'll see that from the examples that were given. So let's write down first a little bit about what the carbon-hydrogen analysis actually is. We'll bring that in, and I'll let you write that down. And then I'll show you an example of kind of a simulation of a carbon-hydrogen analysis. And then I'll show you some pictures of some actual carbon-hydrogen analyzers. You can actually buy a device that will do this for you. Put in a sample of some chemical, let the machine chug away, and if it works out the way it should, technically it could spit out a chemical formula for you, as long as the computer is programmed correctly and all of the devices are working properly. So we've done some examples of some calculations that involve carbon and hydrogen. We've already talked a little bit about reactions that hydrocarbons can undergo, and combustion is one of them, right? So we've done some combustion balancing. We don't need to do that here, but we all know that compounds that contain hydrogen and carbon, when they're burnt, all of the carbon that was in that hydrocarbon becomes carbon dioxide, and all of the hydrogen that's in the hydrocarbon ends up in the form of water. And really, at the simplest level, if we can determine how many moles of carbon are in the carbon dioxide after the chemical reaction, then we can work our way backwards and say, well, then that must be the number of moles of carbon that were in the hydrocarbon itself. So what we're going to be doing is we're going to be given some numbers, masses of carbon dioxide, where we're then going to have to work our way backwards and figure out how many moles of carbon are in that carbon dioxide. And then we can say, hey, it must have come from the hydrocarbon. So we're going to analyze the products of the combustion to figure out how much carbon there is in the hydrocarbon. And from the water, again, all the hydrogen that's in the water must have come from the hydrogen that was in our molecule. We should be able to work our way backwards and figure out exactly how much hydrogen was in the hydrocarbon. We're also going to be doing another type of calculation where instead of it just having hydrogen and carbon in it, it's going to have hydrogen, carbon, and oxygen. Technically, that's a carbohydrate, right? It's got carbon, hydrogen, and then the oxygen. The hydrate part represents kind of water, but it's representing the fact that there's oxygens in there. And so we'll have to do an extra step when dealing with a carbohydrate because it's not as straightforward as the carbon and the hydrogen due to the fact that extra oxygen has to come in during the combustion reaction. So we have to do a special little calculation when dealing with a carbohydrate. Now, just to kind of give you an idea on what I mean by this carbon-hydrogen analyzer, because I'm doing a lot of talking here. Let me show you a little website here. So this is a website that comes from a university or a college in the United States, Davidson there. This is actually the same web address that I have posted on the slide there if you wanted to take a look at it yourself. And it's a little kind of explanation of how to analyze a carbon-hydrogen situation in terms of carbon-hydrogen analysis. There's a lot of an explanation here, but what I want to get down to is the bottom right here. All right. So this is a little simulator to kind of simulate what's involved in a carbon-hydrogen analysis situation. Let me just give you an example of what would be taking place. Let's say then here we've got a carbon compound that contains carbon, hydrogen, and oxygen. Let's switch it to just carbon and hydrogen. Do we have any that simple? Carbon, hydrogen, and oxygen. No, they're not going to give us one that simple. So we'll just take a look at this one here. And so let's say we've got this substance that contains carbon, hydrogen, and oxygen, and we inject it into the machine where there's a furnace, lots of heat, and it essentially burns that substance, all right? And you can see how the furnace is now connected by tubes to something that we would call an H2O trap and then a CO2 trap. So essentially what happens is we burn the hydrocarbon. It creates carbon dioxide and water. Those products kind of move along, and when they get to their particular trap, that particular molecule is stuck inside that little area. Now, how would you catch molecules? Well, there are many compounds that chemists know that exist that are selectively absorptive to certain other molecules. Water vapor is the easiest one to kind of explain. How many people have bought an electronic device only to find that little package sitting at the bottom that says, "Do not eat"? Do you know what I'm talking about? I hope nobody ate it. All right, well, good. You don't want to eat that stuff. So the reason you don't want to is there's a chemical in there that absorbs water vapor. It's highly absorptive to water molecules. And so chemists have known for years that certain molecules stick to other molecules very well. It's probably a polar substance that really sticks to it really well. In your little electronic device, let's say it's being shipped from China in a container that gets cold and then warm, and it's all kinds of different conditions. It's on a boat, lots of moisture, and that electronic device does not want to, we do not want it to get wet. So in that little container, they put that little packet, and it absorbs any water vapor that gets in, keeping it nice and dry, okay? Now, what we can do with a similar type compound is we can pack that compound in this H2O trap so that when we do the chemical reaction, as the carbon dioxide and water come through, the water vapor gets trapped in that H2O trap. And because water molecules are getting trapped, the entire mass of the system gets greater because there's water molecules getting stuck inside the apparatus. We can have a similar compound that will absorb carbon dioxide, all right? And it wouldn't be the same. It would have to have different substance in it, but it could still absorb it. So in this little simulation, I don't know if you can see, but my little scales read 0, 0. And if I say burn the sample, you'll notice that the scales increase as if the simulated carbon dioxide and water are being sent through the system. And we can then measure the mass of the water and the carbon dioxide that's been trapped, all right? So this little simulation is over, and we could actually use these numbers along with these facts to solve a problem. Maybe we can come back to it at the end. If we got time, we can solve this problem. Knowing the masses of the carbon dioxide in the water, we can work our way backwards and find the moles of hydrogen that were in the original sample, because that's the only place it could have come from, and the moles of carbon that were in the original sample. Once we have those moles, we can divide by the smallest number, get a whole number ratio, get an empirical formula, get a molecular formula just like before. All right? I did a little simple search here of carbon-hydrogen analysis, and you can actually, find pictures of devices that would have all those components in it. You would set up the machine, you'd inject a substance, it would go through a furnace, combust, go through those various things. They would have scales built in, and it would simply spit out those numbers for you. You could probably program a computer to calculate exactly what the empirical formula is. No thinking whatsoever. Who would use a device like this? Well, if it was a forensic laboratory and there was a sample of a substance that nobody really knew what it was, a white powder, you could take that white powder, you could run it through the carbon-hydrogen analyzer, and yes, cocaine has a molecular formula that contains carbon, hydrogen, I think some oxygen, and I think some nitrogen, and it would spit out that formula, and you could test it positive for cocaine, right? You've all watched CSI. Have you tested that white powder? No, not yet, boss. They put it in, flashy music, they show the hands working, and the guys looking in the microscope. You know what I'm talking about. 2 seconds later, it's cocaine. And then Horatio takes his glasses off. No? No, anyway. It's the way it always goes. I thought so. Anyway. So these devices exist. We're essentially going to learn how the calculations work in that particular thing. Okay, so let's go back to our PowerPoint here. So in the combustion chamber, we get the carbon dioxide in the water, and then with it, mass spectrometer, and I've just described a mass spectrometer to you. That's how the isotopes were discovered. They send some charged molecules through a magnetic field, they bend, and they can figure out the molar mass perfectly. And again, that device will calculate it out for you. All right, we're going to figure out how to do those calculations. Before we do that, I just want to kind of go over a simple little flow chart on the steps that we're going to use in order to solve these particular things, because they say flow charts make us smarter. And so let's first just kind of go ahead then and kind of come up with, so if we've got here just simply a hydrocarbon, it's got carbons and hydrogens in it, all right? We don't know how many, maybe X and Y. And what are we going to do with that particular thing? We're going to burn it. Again, the classic, what do you do when you want to figure something out? Burn it. And what do you get after you burn that? Well, I'm hoping from our little discussion, you realize that we're going to get carbon dioxide and we're going to get water. And we're going to get so many grams of CO2 and so many grams of H2O. Now, in a formula, remember, the X and the Y is a ratio of moles. So we eventually have to get to moles. So how am I going to convert this grams of CO2 to moles of CO2? Oh, how do I go from grams to moles? Just change the unit. Just change it? What conversion factor do we use to convert grams to moles? Again, those math people, they're so good at indoctrination. Me, not so much. What's the conversion factor that converts grams to moles? Yep, the molar mass. Ooh, where do I get the molar mass? From the periodic table. It's all coming back. That's exciting. So if I have the molar mass of CO2, then I can convert that into moles. Now, in the end, I want moles of carbon. Remember, we had that little conversion factor. How many carbon atoms are in each carbon dioxide? 1. So remember, I can use a ratio of like 1C for each CO2, and that will convert it to moles of carbon. And that's what we need to get, because once we have moles of carbon, we can divide by the smallest number, and we can get back to that ratio up here. So for water, I'm going to do the same type thing. How am I going to convert my grams of water to moles of water? Yeah, the molar mass of what? of water, because I'm dealing with water right now. So I need the molar mass of H2O, because I've got grams of H2O. I want to convert it to moles of H2O. And then I need moles of H. And how many H's are in each H2O? 2. Thank you. It is easy. It is simple. 2 H's for each H2O. And if I do that, I'll get moles, which won't be really nice numbers, but if I divide by the smallest number, I'll have a nice ratio like all of the empirical formula that we've done. Okay? Now that's for a simple carbon-hydrogen or a simple hydrocarbon. But what if we have oxygen in it as well? What do we do if we have a carbohydrate? So this next little flow chart is for a carbohydrate. Everybody have what I've got there? All right, we'll move ahead. And so what if we have in our particular substance this time carbon, hydrogen, and oxygen? What if we have a carbohydrate? This becomes conceptually a little more difficult, and that's because when we burn it, we're going to be adding extra oxygen from the atmosphere, and so we can't just use the number of O's in carbon dioxide and water to figure out the oxygens. I have to do it a different way. So I am going to start the same way, and I'm going to kind of work my way off to the side this time because I want to leave the right-hand side for some room to deal with the oxygen. But again, we're going to burn it. Burn in O2, which is why I can't just take the O's out of the water and the carbon dioxide, because extra O's came in. And so again, I'm going to end up with grams of CO2, and I'm going to end up with grams of water, and I'm going to do the same thing. I'm going to use the molar mass of CO2 and get moles of CO2, and I'm going to use that ratio, and this time I'm going to just write it as 1 to 1. I think we've used that ratio quite a bit. If we want to simplify it, that's fine, 1 to 1, and that's going to get me moles of carbon, which is what I need. I need moles of carbon. And I'm going to do the same as I did on the last slide, molar mass of H2O. That's going to get me moles of H2O. And again, using a 2 to 1 ratio, that's going to get me moles of hydrogen. Okay? Now I'm going to change color here on my little animation here because I just want to change gears a little bit. The next step in solving a problem that has carbon, hydrogen, and oxygen is to turn those moles of carbon back to grams of carbon. Now notice, it's not grams of carbon dioxide, but just grams of carbon. How do I turn moles to grams? What's the conversion factor called? I'm asking the same things over and over again, by the way. Yes? Molar mass. But this time, it's just carbon. So I'm going to use the molar mass of carbon to get me grams of carbon. Now, those are the grams of carbon that are found in the carbohydrate. I'm going to do the same with hydrogen, and that's going to get me grams of hydrogen. Yep. Sorry? Molar mass with a little hydrogen, molar mass with a little carbon. Okay? Now, I've left one important part out. When you do a carbohydrate analysis, you will be given the total mass. You have to be given the total mass of the substance. And the reason you have to be given that is because it's the only way we can determine the amount of oxygen that's in that substance. Because now at the bottom, I have mass of carbon, I have mass of hydrogen that's found in here. I'm going to be given the total mass. How do you think I could find the mass of the oxygen that was in that original substance? CJ? Yeah, take the total mass, subtract off the carbon, subtract off the hydrogen, and then you must have the oxygen that's left. So when you have a carbohydrate, you do it the same way as a simple one, but now you've got to do some extra calculations on the side. Mass of oxygen. will be equal to the mass total, and that says TOT, total, minus the mass of the carbon minus the mass of the hydrogen. Okay? Once you have that, you can then take that mass of the oxygen, and with its molar mass of oxygen, you can get moles of oxygen, and now you've got all three numbers. Now you're ready to divide by the smallest, find the whole number ratio. If you're given a molar mass, figure out how many empirical formulas are in it. Okay? These questions really are good to measure true understanding. The questions we've done up to this point, you could memorize the steps, probably get away with not really knowing what you're doing, and still get some numbers out of this. But with all the steps involved in these types of questions, you really need to understand what's going on. These really separate out what I would call the contenders in our chemistry class versus the pretenders. Get it? Contenders and pretenders. All right, let's do some examples. This PowerPoint is online. I'm also going to save the writing that I've done here, and I'll put it up online. It'll simply say with notes on the back end, and I'm actually recording all the writing, and I'll put a video up as well. So this is an example of just the hydrocarbon, no oxygen. So notice it tells us carbon and hydrogen is burnt, which means we don't need all those extra steps to find the oxygen. We also have a molar mass. So in the end, we can find a molecular formula. So what I'm doing, or what we're doing in all of these questions, is we're getting an empirical formula, but we've got to go through extra steps to find the moles of carbon and hydrogen. But it's just like an empirical formula problem. And then if we've got a molar mass, we complete it with finding the molecular formula. So again, just like any of our empirical formula problems, start with the information you're given, but now you'll notice it's water and carbon dioxide, so 3.94 grams and H2O times. I need the molar mass of H2O. We've done that quite a bit. I don't need to see it every time. It's 18. I think we're okay with the fact that it's 18, right? If you need to write it down, by all means do that. But it is 18 grams per 1 mole. And I'm not done yet, because that's going to get me now moles of water. So I now need that ratio of hydrogens in water. And how many hydrogens in each water? 2. So we're getting pretty good at this. I would be okay if you just wrote this, 2 to 1. Right? If you feel you still need to write 2 hydrogens in 1 H2O, then by all means write it. But if you're comfortable enough that you know that I need the 2 to 1, that's great. And if I do that entire calculation, I'm going to have here at the end moles of hydrogen. and I'll take that number once we get it. And again, make sure you can get this number, even though some people are giving it to me quicker than others. John, what do you got? May you borrow a calculator. Excellent. Keep in mind, I am recording this. That's Jonathan. Thank you. No problem. What do you got? 0.438. Excellent. Moles of hydrogen. And we will do the exact same situation except now with the carbon dioxide, 9.62 grams CO2. CO2 is another one of those molecules that we use over and over again. If you haven't done that for a while, 16 times 2, 12. What is the molar mass of carbon dioxide, TJ? 44.0 grams per mole. Grams are on the top, and I just erased that somehow. What's going on here? Don't die on me now. 44.0 grams per 1 mole. What's our ratio, carbon to carbon dioxide? 1 to 1. And how many moles of carbon was in this original hydrocarbon before it was burnt? Well, it's still the same moles of carbon. Just got to keep track of it. Here, look at here. 1 carbon in each carbon dioxide. We're not looking at the oxygens, right? So what do you have for a number? Yep, Jess. 2, oops, stick with 1 in the middle maybe. 219 moles hydrogen. So now we're to the point where we're dividing by the smallest number, make it a whole number ratio, whole number ratio. I don't know where I can fit that. Let's just get this, block this out of the way. So here I'm going to have 0.438 divided by 0.219. 0.219 divided by 0.219. That's going to be equal to 1. Is that 2 up top? 2. So our empirical formula is, and we usually start with the H's. We usually start with the C's because it usually goes CH something. So C1H2. All right? Now notice we've got a molar mass. So the step I taught you on Friday, determine the empirical formula mass. 1 times 2, that's 12. What is that, 14? 14 grams per mole. Molar mass divided by the empirical formula mass. (84 over 14). 6 of them. Therefore, the molecular formula is 6 of those units, right? C6H12. C6H12. So other than dealing with water and carbon dioxide and the little ratio to pull the hydrogen and the carbon out of it, it's a standard, regular empirical formula problem with a molecular formula problem on the back end. All right? Let's do another one. This one now has some nitrogen in it. And when the nitrogen was burnt in a very hot furnace, this produced nitrogen dioxide, which means we'll just have another, equation for the nitrogen. We'll get the hydrogen, we'll get the carbon, we'll get the nitrogen that's in the formula, and we'll Again, divide off the smallest numbers. The process is identical. Divide by 44, 1-to-1 ratio, or divide by 18, 2-to-1 ratio. So you should be able to, once you get your numbers down, fairly quickly run across and find the moles of carbon and the moles of hydrogen. 16.6 grams of water. Again, go on ahead of me. Don't wait for me. The same equation that we did in the last one running across the top, except we just have a new number. Molar mass of water turns it into water. 2-to-1 ratio turns it into hydrogen. Moles of hydrogen. Somebody have that number? I'm hoping, TJ? 2.08. Okay. 2.08. 1.84. What did we not do? Did we divide? I don't know what, 1.84. I have no idea what you did. We're dealing with water, right? So same thing with the carbon dioxide, 28.4 grams CO2. Notice how sometimes I drop off that 0.0 because I know that it's there. I still know I'm dealing with 3 significant digits. So if you do that, make sure you keep your 3 significant digits. 1-to-1. How many moles of carbon? Yep, Jess? Now I've got a new number in here. It's 8.49 grams nitrogen dioxide, NO2. And if you've gone ahead of me, you know you need the molar mass of the nitrogen dioxide. Does somebody have that? 46? It's essentially the same mass as the carbon dioxide, but we got a nitrogen instead of the carbon, which makes it a 14 instead of a 12. And again, how many nitrogens in each nitrogen dioxide? So again, 1-to-1. John, you got that number? And that's moles of nitrogen. Now we're back to where we were when we did any regular empirical formula. Divide off the smallest number, get a whole number ratio, check the molar mass, see if we've got to multiply by anything. So 0.185 appears to be the smallest. 1.84 divided by 0.185 is looking really close to 10. And the only one that I don't have is that middle one now. What do we got? 3.5? Which means, what are we doing with all our numbers? Yeah, we're doubling. Again, remember, at the empirical formula step, you can do the double to fix, but not at the molecular formula step. It's got to be a whole number. So that means our empirical formula is equal to, what do we got? I like to put the C's first because that's just the way I'm used to it. You don't have to. C7, is it? H20, and then N2. That's getting a little busy on my slide. I'm going to change colors just so that we can see the rest of the problem just so that it's a little clearer. So we need to come up with an empirical formula mass here so we can compare it to that 264. 14 times 2, 1 times 20, 12 times 7, 132? 132 grams per mole. So again, we always need that molar mass, that big number, over the empirical formula mass. For those who like formulas, I'm writing it in. For those who don't need that, can see where the end of the question is heading, that's fine. 264.0 divided by 132. And that's looking like a nice 2 right there. Which means then our molecular formula, oops, let's get the color right here. Which means our molecular formula is, and I've got to then multiply everything by 2. That makes a C, goodness, 14, right? H40, N4. All right? Yeah, it would be a big one. Who knows? There could be all kinds of different ways that that's drawn. But yeah, that would be it's a big molecule. I do not. There's many molecules that could fit that because of the different ways you could make those connections in carbon. If you stick around for the grade 12 university, when we do the organic chemistry, we'll talk about all these different ways these complex molecules can go together. Yeah, right here, we're just happy with that formula. Okay? So I'm going to do one more example, and that's the most complicated one. That's the carbohydrate where we have to then go back and subtract off and get the oxygen. Okay? Right there, and there is the question. So notice in this question, I have to give you the mass of the entire substance at the beginning. That's because we have to do that subtraction. We start it the same way. We've got to get moles of carbon and moles of hydrogen, and then turn that into a mass. So you're going to start it exactly the same way. So when you have a carbon-hydrogen analysis problem, you're always going to those same numbers over and over again. It's very repetitive. I'm not worried about the total yet. That's going to be at the end. So I'm going to start with my carbon dioxide. Let's put some color on that. 1.50 grams CO2. And I'm hoping you're sensing the repetitiveness. I just finished making the test up and I wanted to change some numbers in some of the questions to make sure that you don't just completely memorize a question from an old test. And it takes me no time to quickly come up with those numbers because I know I'm going to be dividing by 44 in a ratio of 1 to 1, right? Boom, boom. You do it enough times, it becomes, second nature. You could even be as lazy as to write down this. But I don't necessarily recommend it because I like to see, for some of us, we're still looking at, okay, grams at the bottom. But after you do it so many times, you realize, oh, I got to divide off that molar mass, 44 on the bottom, right? 44 and 1 to 1. Same with the water, 0.405 grams. I write down the H2O. The only reason I write down the H2O is to remind me that I need a 2 to 1 ratio. So again, if I were doing this myself, I'd just put 1 over 18 times 2 to 1, right? That's what I'm writing because I've done it enough times. I know exactly what I need. And if you're there, you're able to do that. Excellent. That means you're getting this to the point where you're doing this well. And I'll take those numbers because we need the moles. I could just attach on another conversion factor to convert the moles of carbon into mass of carbon, but we need the moles in the end, so I'm going to write them down. Jess, what do you got? I'd like one more digit again. We're dealing with 3 significant digits, so 340? 341? So 341, and that's moles of carbon. And sorry, what was the second number? 0450, and that's moles of hydrogen. Okay? Now, because this is a carbohydrate, I'm going to change colors again. I'm now going to just put a conversion factor on the back end of this to turn it into grams of carbon. How do I turn moles into grams? Molar mass. And this time, it's just carbon. So what am I putting here? What's that? 1 over 1? No, that's not a molar mass. It's definitely not a molar mass of carbon. Yep. 12 grams per 1 mole. That's going to turn my moles into grams. Molar mass of hydrogen. 1. 1 gram per 1 mole. 0.0450 grams of hydrogen. And how many grams of carbon are in this thing? Yes? 409? Nope, that's good. So now I want the mass of oxygen. How am I going to get that? TJ? I'll do them as separate numbers. 409 minus 0.0450. I'm subtracting them both off. I didn't make a formula for that little line, but I hope we understand what I've done here. I'm taking the total, subtracting the mass of the carbon, and subtracting the mass of the hydrogen, and the mass of the oxygen must be the only thing that's left in that substance. Jess? Grams of oxygen. I ultimately need moles of oxygen. So I need a molar mass to turn that oxygen into moles. I'm going to change back to my yellow because we're getting back to looking at moles. Times what goes where? Yep. Yeah, 1 mole, 16 grams. And so how many moles of oxygen are we dealing with? TJ? 0.0341. And that's moles of oxygen. Now we're ready to do our dividing, except now our equation looks pretty messy, right? So we got to kind of pick out the 3 numbers we're looking for. There's our moles of carbon. There's our moles of hydrogen. And down here in the corner here, there's our moles of oxygen. And I'm totally out of room, so I'm going to go to the other page. The smallest number appears to be 0.0341, and there's 2 of them. It looks like it's for carbon and oxygen. So I'm going to switch pages here. So for carbon, oops, I'd like to be in yellow again. That's okay. 0.0341 divided by 0.0341. Is that correct? And then we've got hydrogen, which I can't remember the number, and oxygen was also 0.0341, wasn't it? And that's a 1, right? And what was the hydrogen number? 0.0450? 0.0450 over 0.0341, and what is that? 1.32? And I'm going to say, hey, that's pretty close to 1.33, close enough for me, you know, we're it's right there. So what am I doing with these numbers? Times 3, times 3, times 3. Remember, we're at the empirical formula step, so we're still able to do that. And therefore, the empirical formula is C3. What have I done? Oh yeah, C3H, and my H is horrendous here. What is that? 4? C3H4O3? O3. Yeah, that's what it is. That's what our numbers are telling us. Got to stick with it. Do I have a molar mass for this question? Yeah, so I need the empirical formula mass again. Just, sorry? Molar mass over empirical formula mass. I don't know what it is because I can't remember the question. 176.14. Lots of significant digits there, but I don't think we need them all. We're looking at 2, right? Beautiful. 2. That's what we like. Therefore, molecular formula is. So I'm doubling everything again, right? C6H8O6. All right? And you can see down here at the bottom, your homework is the question sheet. All right? Let me just do something here for a second before we continue here.